everyone. Today, Hattie and I are going to present the Towards Real World Blind Face Restoration with Generative Facial Prior research paper. So the research paper by itself is pretty long and complex, but we tried our best to break it down into understandable chunks and give you a whole overview of how and why this GFP-GAN was brought to existence, as well as give you a high and low level explanation of the model. And then we're going to share the results and say whether this paper is going to be applicable for our case, and we're working on implant detection. So for people who are not familiar with computer vision, image processing, and stuff like that, these terms, blind face restoration, facial prior, probably scary. And I totally understand that. And let me clear it out from the very beginning. So a blind face restoration is a technique that is used to restore a low quality images to a high quality image. And that is pretty much it. And a facial prior is an ability of a model to stay within the shape of the face. So yeah, that is pretty much it. Let's go ahead and talk about the two approaches that were used before the GFP-GAN. And here we are. The first one is the geometry facial prior, which is in simplest words means that if we have low quality images, we're not going to have good results. Why is that? It's because this specific approach focuses on facial priors that we talked about earlier. And the overall thing is that the overall tendency is that whenever we have as low noise as possible, we are going to have a good representation. However, when we have more degradation, it means that we're going to have a worse result. And one more disadvantage of this approach is that whenever we have the small details such as hair and, for example, eye pupils and stuff like that, the model cannot make good results out of it. And the second one is a reference prior. What it is, as it can be inferred from the name, it has to do something with reference, right? So this particular approach relies heavily on high quality reference images, such that the dependency on the degraded inputs is as small as possible. But in the real world, especially in our case, it's really hard to get like a good amount of reference images, and that is why it is extremely impractical in the real world scenarios. Because when you don't have enough high quality images, you're not going to have really good results. And because of that, because of the reasons that were just mentioned, we can kind of build the idea that generating accurate images is not a piece of cake. And in particular, these approaches, the researchers typically use GAN inversion, which is basically inverting the degraded images back to a latent codes of the pre-trained GAN, and then conducting expansive image-specific optimization to reconstruct images. So what it means is that it's extremely expensive and it requires a lot of time to optimize and find the proper parameters. And that approach actually gives good results, but the fidelity and the ability to produce the smallest details, such as eye pupils or I don't know, like lashes and stuff like that, is extremely hard. And that has an explanation, is that the low dimensional latent variables cannot give accurate restoration. And that brings us to the topic of today's research paper reading session, the generative facial prior GANs. What it does differently is that it already has a pre-trained face GANs that are used as facial priors. And it achieves a good balance of realness and fidelity in a single forward pass. It mainly consists of the degradation removal module. As it can be inferred from the name, it removes all of the degradation, such as noise and blur and JPEG compression, stuff like that. And also it uses pre-trained phase GANs, which are connected by direct latent code mapping and several channel split spatial feature transforms, which are going to be explained by Hattie in just a little bit. Just to give you an explanation, a very simple explanation of what this model is about, it basically gets an input X with the image that has a lot of degradation over that, and it tries to make as accurate output Y hat, which is which is which is really close to the image Y, to the ground truth image Y in terms of realness and fidelity. And that is pretty much what it is about. And I'm gonna give the stage to Hattie to explain the model's behavior in deeper understanding.
Okay, so like, let me share my screen. Okay, I'm audible and you can see the screen, right?
Yes.
Okay, cool. So like, as Dinora mentioned, like the model, it's quite complex, but like if you take one element at a time, you can understand it. Like the first element of the model is a degradation removal model. What do I mean by it? It's like this blue chunk over here. And like, if you ever heard of UNet, it's for here, they used UNet for this. And UNet is basically as encoder, like autoencoder type of model, but just with skip connections, and mainly used, it was first used for medical field. And the idea here is like to go from low resolution image, which is like the input, map that into low dimensional space, latent space, and then go back to a higher dimensional space. And the hope is like, while doing that, going from the input space to the latent space, is like you'll only keep the relevant information, and you will get rid of any kind of high level degradation. And then and like that's kind of the idea. And UNet do this by increasing the receptive field for large blur elimination, and by generating multi-resolution features. And what do I mean by this? Because technically, when you go deeper, by default, you're increasing the receptive field. And while during this approach, two variables are kind of created: f-latent and f-spatial. And like, just keep those in mind for now, because they're going to be used later technically. Okay. For the second step is like moving those f-latent and f-spatial to the next step, which is like the pre-trained GAN. Over here, they use style GAN too. And the idea is like, take the latent variable from the latent space, map that into the style GAN using multi-layer perceptron, like just linear layer. And the hope is, because the style GAN won't be trained technically, you kind of give the f-GAN, give the style GAN the closest latent variable to that face. So you will have kind of close image to what you have as the input. The second part is like using the f-spatial. What are the f-spatial? It's like just the features produced by the decoder in the UNet. And those are used why? Like what the f-GAN is going to produce is technically going to be modulated using the f-spatial. What do I mean by modulated? Is like conditioned. What do I mean by this? It's like the f-spatial gonna help you produce some kind of transformation in order to transform even more the image of the style GAN in a way that you get it even closer to the input image. Because at the end of the road, we want something as close as it is to the input image, but like higher quality. So kind of that's the idea. So, and one nice trick is like, while doing the SFT, which is like the style, the spatial transformation, they don't do it to the entire feature, all the features. They technically split into two chunks, the features into two chunks. Let's say we have like 64 features produced by the GFP-GAN. 32, they will pass as they are. Just 32, they will have the transformation. And that's interesting in a way because you reduce the computation. That's one thing. And from second part, you'll be using the features from the produced by the GFP-GAN as they are, and the features used by the unit. And that's quite interesting because it increased the fidelity of the model overall. Kind of the last part is the losses, and in my opinion is like the best part of the model, because here they use like 5 losses. The first is the reconstruction loss. What reconstruction loss kind of even contains 2 mini losses. The first one is L1 loss, like just absolute error, and the second part is perceptual loss. And what is this? The perceptual loss is like take your input image and take your output image, pass those two into pre-trained model. I guess here they used VGG19, and then just the L1 loss between the embedded. And of course, it's weighted. So that's kind of the reconstruction loss. The second one is the adversarial loss. It's like to encourage the GFP-GAN to favor the solution in the natural image manifold and generate realistic textures. What does that mean? Technically, you just want to see how realistic your produced image. The third part is facial component loss with local discriminators. And over here, the produced region of interest are going to get cropped. And for the context of the model, the region of interest are like the eyes and the mouth. So technically what happened is like the eyes and the mouth, they get cropped and pass into discriminators, and to see how realistic those patches are, those specific patches are. And another interesting thing, like other than this kind of adversarial loss, they also represent feature style loss. And if you're familiar with NST, neurostyle transfer, it's kind of, the idea is to use the Graham matrix for using the features of the trained discriminators in order to kind of quantify the difference between this style. And what the style technically is the feature correlations. So yeah, the identity preserving loss is kind of relatively like the perceptual loss. Is like you take the image through an embedding, and then you kind of take the difference of the embeddings. The third one is the restoration loss. And I found this to be really interesting. It's my first time seeing this kind of usage. Technically, you remember the UNet over here. As I said, like there is kind of multi-resolution features, right? So technically what they do is like each layer gonna produce something, and they want that something to be as close as it is to the input. So they take the L1 loss of that output and the input. And that's kind of make them 5 losses all in all. And that's, I found it like quite interesting. So I guess like I'm passing again, Dinara, the word.
All right, thank you so much. And let's finish it up by showing the results and whether this paper is applicable to our implant identification project. So first of all, about the results. Overall, it's doing a lot better than the previous models that were introduced. It has the lowest LPI-PS score, which stands for Learned Perceptual Image Patch Similarity, which is basically it shows how the image, how the predicted image is close to the ground truth, and also it achieves the lowest FID and NIQE scores, showing that the output have close distance to the real phase distribution, which is a very, very, very important scores to keep track of whenever you are restoring images. And I especially want to focus on these images over here, is that as you see, when it's zoomed in, it gives a very good realistic image as a result. And that is exactly what I wanted to show. I wanted to show how it looks like when in comparison to the other ones. And as you can see, the GFP-GAN is doing a very good job. And especially over here, especially on the last row with the image where the input has a closed eye, and the previous models were, I'm sorry, we're not really good at reproducing or restoring even a closed eye. So I think it's a very important step in restoration. So yes, at the very beginning, I've tried to put a big accent on that the model was carefully designed, and that is exactly what is going on over here. So the model itself has a lot of things that a lot of components over there, and the researchers were trying to show how it looks like when you remove some components over here. Overall, we can see that the accuracy, the error rate is increasing drastically, except for the case where we're using SFT without the channel splits. So when there is no channel split, it preserves the identity, but it has an overall bad fidelity. And that is exactly that exactly explains why there is a degradation that is lower than in the previous, in the original GFP-GAN model. And here are the results in comparison to each of them. And I think we have a clear winner over here, that it has a realistic image that represents, that looks real. So of course, not there are no perfect models, and it has its own limitations. And the limitations are the following: that they still need to have a more balanced and diverse data set. And because of the lack of that, there are two problems that are arising. The first one is being that the grayscale images are not biased. So it cannot infer skin color, and it has to have a more representative data set. And also one more case is that whenever the image has a very severe degradation, it cannot make a very good output, as you can see over here. So I think the last thing that we need to talk about is how is this project, and if this project is applicable to our image identification. To say shortly, no. And to explain why it is basically because the model itself relies heavily on the pre-trained phase GANs, which were trained on the style GAN 2, and our case is not, our domain is a little bit different because we're working with medical imaging, and it might require us to use another model. And secondly, as Hattie was talking about the losses, there was one that focuses specifically on the face regions. For example, if you remember the image where it had an accent on the left eye and right eye and the mouth and stuff like that, this kind of losses would be a very big trouble to train it on our model, on our images. Oh my God. So it would require us to change a lot of parameters. However, it gave us a very good idea of using super resolution, because as you can see on the right, we have a lot of images that are suffering from severe degradation. And we believe that using this approach of removing the noise, as much noise as possible, would boost the overall accuracy of our model. And that is pretty much it. I hope you guys, I hope we gave you some understanding of GFP-GAN, and thank you so much for listening. And if you have any questions, please let us know.
Yeah, please, if you have any questions regarding any part, anything that you didn't understood, because like we made sure that we kind of have a deep understanding, not a lower understanding of what the paper is. So please, if you had any question, feel free like to ask it. Okay, guess like there's no questions. That means like we're done.
Yeah, I guess so.
Okay.
But if you guys want to ask something, you can always DM us. We are pretty much always on Slack, so you're free to text us.
I have a question.
Sure.
Yeah, sure.
I wanted to know, was the GFP-GAN trained just on faces only? Like, are there did they try it on like other body parts, like on a full sort of like a picture where you have legs and
Okay. So like as a concept, let's say like it's general face prior, I guess, generative facial prior. So like it's used on faces mainly. And even like they tuned the model. Like, let me share my screen. Okay. Let me go to the, yeah. So they technically chose the model and the losses and everything in order to make it work on faces. That's one. But like the idea is, if we can change like some few stuff about the model, like the pre-trained thing, because here it's pre-trained, like the GAN is pre-trained to generate good faces, right? But like hypothetically speaking, theoretically speaking, you can train a GAN to generate good anything, good bottles, good products, goods, I don't know, animals, whatsoever. So the idea is if you change what this GAN is pre-trained on, and also if you change the facial component loss to like your relative kind of, you decide what components are relative for you and what do you want to focus on, or even omit this loss at all. So theoretically speaking, it would work. But the thing is, did the researchers try it on other thing? No. I hope like that answers the question.
yeah, it does.
Yeah. Cool. So any other questions? Okay, guess we're done.